let's get going. Let's see. Find my probability sheet. Assessing normality. Where's my probability? Variance. Oh, there it is. All right. So, get going. Let's get started. We've got review of this Bayes theorem. All right, so I've got this up here. All right, the whole focus, the whole reason we introduce this is, we're interested in the probability that we actually have a condition if a test comes back positive. All right, so you'll find it written like this in textbooks, probably online, where it says the probability of A happening given B is equal to probability that A happens times the probability that you'll have B given A over all of the times that you could have B. All right, and it kind of expands out to this description. All right, and we have some rules, but I say know this box. I say know the box, but I think a slightly better way to know it is if we change it from like A's and B's to our condition and the results of the test. All right, so let's kind of revise that equation so we can have it written down and then go on. All right, so our condition will be either yes or no. All right, and our test result will be either plus or minus. Okay. So using those, then what we're looking for is the probability that we actually have a condition if we have a positive test. And that is going to be equal to probability that we actually have the condition. The probability that we have the condition times the probability that we're going to test positive if we have that. So we set it up. In order to test positive, we have to have that condition. And our probability of actually testing positive is based on whether or not we have a condition. This is our conditional probability. And that's going to be out of all of the times that we can test positive. All right? Well, what are the ways in which you can test positive? Well, we can test positive if we have the condition. So we have the condition, and then we test positive. Or we don't have the condition, but we still test positive. Right. And we can go a little bit more to say the probability of no is 1 minus the probability that we actually have it. So it'll be, it's not like, well, maybe we have it, it's yes you have it, or no you don't. All right, so these are kind of the equations that you use it and reference anytime we work with a problem like this, with these problems. Any of these Bayesian problems, the tests in the condition type situation. So I asked you to work through the quad test. All right, so the quad test is used potentially to determine if a developing fetus has Down syndrome. All right, it's an invasive test
could be recommended by the doctor, and this information we want to go through is if you test positive, then what's the probability that we actually do, that the fetus has Down syndrome? So, head back to the board. And we'll work through this.
Notice if you did do it. Alright, so what? What? We said test is 81% sensitive and 5% false positive. So our condition, no and yes, and our test results, negative or positive. Right, so false positive we said is 5%. And it's going to sum across the rows because if we don't have the condition, we've got a probability, 5% chance that it comes up positive, and that means we have a 95% chance that it does not come back positive, or that 95 that it comes up negative. Then we have our sensitivity at 81%, so 0.81. So if we have it, we're going to test positive 81% of the time, which means we do not test positive 19%. And we also say the probability that we do have that condition, the probability of yes, is based on the frequency in the population. So it's 0.1447, which is 0.001447. That's 0.1447%. The probability is 0.001447. Now that is the probability in our entire population. So we ask, what's the probability that we actually have it if we have a positive test? All right. So first thing we're going to do is calculate the probability that we have a positive. We're going to use this equation. So the probability that we actually have it is at 0.01447 times the probability that we're going to test positive, 0.81, plus we're going to do probability that we don't have it, so it's 1 minus that value, which is 0.99875 times our 0.05. So there's our false positives. And when I do this, I get 0.05095. So about 5% of the time, we're going to come back with a positive test. Now we want to know out of these 5%, what proportion will actually be a true condition. So now we're going to fill in our numbers. So our plug and chug. And with that, I get 0.02. 2% chance. Is it worth it to get this test? 2% chance? If it comes back positive, 2% chance? Let's do it. Yeah, so that's going to be dependent on the risk. So this number was out of all birds. Out of the whole birds. We can change it. That's why I had the graph up there to show you, the percentages based on ages. So this is a really low number. What is, if we go up to 40 plus, it's 100. We'll do 120 out of 10,000. What is that? 120 out of 10,000. Which is solar power. Over 1,000.012. So
if we change it to a 1.2% chance of having it, how does that change our numbers? Try it. 0.012 times 0.81 divided by 0.12 times 1 plus 98.8. Then yes, given a positive 0.1. It's not the greatest. And we can talk about why isn't it. I think it really comes down to these two numbers. Since our risk is low, I mean, some would say 1.2% is actually a high risk, more than 1 out of 100, right? But it's not like a 1 out of 4 risk. So you're going to have a bunch of actually no's in our data set, and you're going to get 5% of them testing positive, giving that false positive. And then those few yeses that you actually do get, we're only capturing 81%, so 19% of them go undetected. So it's kind of twofold problems. If we're trying to improve our test, well, if you start narrowing it down to the risk factors, that this is just age, maybe we look at some other things and improve this number instead of 1.2. Maybe it gets to 20%. Right, so now it's a 0.2%. Now we're starting to get much better to where if the test comes back positive, then we're starting to increase our chance that we actually do have a condition. Questions? All right, we're going to do another one, more practice. This is the one. This is the area that I think most students have problems. Should use coding tests, but I have this one up here. Cozart microplate EIA enzyme linked immunoassay detects cocaine in your blood. All right, and it was developed because right now the law enforcement pulls you over, they think you're intoxicated or you're driving under the influence. They can give you a breathalyzer on the spot, and the breathalyzer is actually pretty good. It matches up well with blood content. Sometimes, depending on what you last ate, you could throw it off, but it's pretty good. If that comes back negative and you're still exhibiting impairment, what's the next step? Well, haul you down, draw a blood sample, right, to test that. Well, group came up and said, well, let's try to develop some of these quick tests where you can take a swab of the mouth and very quickly know if an individual is high on drugs. And in this case, it's cocaine. So they developed this kit that's easy to keep in the back of a patrol car. You can administer to individuals, and it'll tell us if you have it or you don't. All right. So on this test, they needed to figure out what the sensitivity and specificity is. And that is the purpose of this paper, is to report how good it does, how bad it does. All right, so in order to come up with sensitivities and specificities, they looked at, they actually drew blood from these individuals, and they did a swab, and they tested the blood, and no matter what you answered, whether, I don't use cocaine, blood test doesn't lie. That's actually pretty darn good. So, in the study, they had 602 cocaine negative, 866 cocaine positive. That was their study. All right, from those numbers, they estimated their sensitivity at 92.2% and their specificity at 84.4%. All right, so if we assume that these numbers are the actual numbers in our population. Then what's the probability of testing positive for cocaine? So actually, let's look it up. Percentage of adults who use cocaine. Let's see what it looks like. What is the scope of cocaine use in the United States? I don't want high schoolers. Right? Now I want. There it is. A 12 or older, 0.6% of the population. How about this? Age 18 to 25. That is your age group. So 1.4%. We're going to say 1.4% in the population uses cocaine. So you are out on the town this weekend. I don't know what's going on this weekend. Anything? BioBlitz. That's what it is. BioBlitz. On the way back to BioBlitz, Zoe gets pulled over by Texas Highway Patrol. And she goes, the patrolman or woman says, okay, I think you're under the influence. Breathalyzer clear. So she pulls out this kit, swabs you up, comes back positive. Hauls you down to jail. You're like, I didn't do it, I'm innocent. So you have to appear before a judge. We are going to work through this problem to give her the evidence she needs to get off. Right? So we're going to use 1.4%. I want you to work through probability that the test comes back positive if that yes is 1.4%. Let's write that on. 1.4. All right, 1.4%. Those are our numbers. So let's work through it. So I'm going to need my calculator because I didn't use it. Here's our cocaine test. We said probability of a yes is 0.014. That's 1.4%. Our test is 92.2% sensitive and 84.4% specific. So sensitive is our true positives. That's 0.922. And our true negatives are the specificity, 0.844, which means we have 0.156 as our false positives. Alright, so the probability that we're going to test positive is the times that we actually have it, use it, 0.014 times 0.922. So we're using cocaine and that test comes back positive. We're going to add it to the times that we do not use cocaine. That is 986. 0.986. But we still get that positive. So, probability of that test coming back positive is 0.014 times 92 plus 16.67. 0.16672. So
16.7% chance that it comes back positive. That's why they got you. 17%. So let's see. Yes. Probability that he actually uses cocaine if it comes back positive is that top number. So this first part over total number of positives. Right, so 0.04 times 92 divided by answer. That's how you get out of it. So, 7.7% chance to have it. That's not even over 50%. What's the beyond reasonable doubt? Like what, 50%, right? We're not even. We're so far from. So, why is it that low? Well, again, we're in our population. We don't have a huge number, just overall, on cocaine. So all of those non-users, these non-users, are still, 15, almost 16% of them are still going to come up with a positive test. You've just like inundated the overall test results with a bunch of these false positives just because our overall probability tests are using cocaine. We've got a much better result if we're actually using cocaine. Yes, 92% we're going to test positive. That part's pretty good. We got all these false positives, and that's what you kind of rest the argument. Is, look, the test isn't that good. We've got all these false positives. All right. How do you get on? And this is not a reason to start using cocaine. Stay drug free. All right. Do we need to go over any more of these? I mean, I can dig up more examples. And there are a couple examples on homework. Let's see if I need to get back to the board.
Can you do an example like on your own for 5 minutes and then you run through it for it?
Okay. I left my notes. All right. Yep. So that's what we can do. Got another one. A disease test. This is also might be relevant. College age kid, young adults. Okay. This cleared out. All right. So this test. It's hard to get some of the numbers, but CDC has loads of these diseases, right, especially STDs. All right, so nationwide estimate at 2.4 out of 100,000. That's just nationwide, and again, you can kind of change based on risk groups. But we'll use that nationwide. This is probably, oh, actually, let's use Texas. That's a little bit better. Note the number 2.4 in Texas in 2050. 8,385 per 100,000 people.
When you said better, you mean a lot worse.
Yes. And this is in this, yeah, 8,385. That was off the Texas health pitch. All right, so with syphilis, there's two different tests that can be run. All right, one is the primary test. Primary test, it's a quicker test, a little bit cheaper test. If that comes back positive or questionable, if someone questions it, then they prescribe a second test, which is much more accurate type of test. Now we're looking at actual antibodies in your blood to confirm that they have it. The first one's the antigen, the second one's the antibody test. All right, so for the primary test, our information, primary test, sensitivity is 91%. Specificity is 95%. That's a primary test. The secondary test really isn't a whole lot better, but running both of them together will be much more reliable. The probability to get both of the tests positive, if you have it, is going to be really high. Just the probability that you get a false positive on both tests is pretty low. So there's our information. What I want you to do is figure out what is the probability that we actually have syphilis if our primary test comes back positive. All right, we'll give you a couple minutes. I don't think that 8,000 was throughout. I think that was like total number of positives. It wasn't like the actual rate that you have. Find that number.
questions like this on an exam, will you give us that formula? Or is
Yep.
that something we need
Yeah.
to?
No, I'll give you the formula. So yeah, on exam 2, you'll do a problem like this. Yeah, it's not on exam 2 because we won't have a chance to do the homework and get it back and answer the question. Yeah, we should probably change the numbers. We'll work that. That's a little high. It's kind of a lot high. So in 2018, in Texas, total number of syphilis cases was 12,900, which works out to be about 44.9 individuals per 100,000. That is total. So that includes your primary and secondary syphilis, which are like when transmissible, and that includes also congenital. So a mother can pass it to newborn offspring, and late cases which have it, you just don't. You're not exhibiting any sort of transmission. Okay, so there it is. 83, 85, 2015, I had 84, 40 now, so I must have taken some out. Males are much higher risk. All right, so did you get it? Work through this. Sure. Great, work through this. Sensitivity, 91%. Specificity, 95%. 5% false positive rate. Our guess is. All right. 8 point. We'll do 8 point. 8.44%. All right, so probability of testing positives will be situations where we have it and we test positive. Times we don't have it, it still tests positive. Here, 105. Yeah. Probability have it if we test positive. Answer
Yep.
I wonder on the top line after the plus the 0.916, I had that as 0.95.
So after the 0.916?
No, so you have the plus sign.
Yep.
And then the 0.916, I had it 0.95 times 0.95
So where'd you get the 0.95?
from the chart. No, no negative.
So this is, we're using this. So the yes was 0.084, so you have that, right? The probability that you don't have it then is that 0.916. Oh, is this number wrong? 0.084?
That's right. I just wasn't understanding where you got the 0.916.
Yeah, so this is our yes. That means our probability of a no is that 1 minus 0.084, which I get as 0.916. So we've got our probability of being yes, and the probability to test positive, and this is our no, this is our positive, if it's our false positive. Now we can correct it, and again, based on risk factors, probably should use more appropriate number. The probability of actually having it in the population is going to be low, which means we'll still have, these false positives, but you can kind of get rid of that by changing who you test. Males are looking at that. Males are just, the majority of the cases are in males. 6,000 versus like 1,000 females. So that, plays a role. Age plays a role. History, behaviors play a role. So, all right. Questions on that?
So it's not a percent when you divide by the 100,000.
It's just a yeah. Did you?
Yeah. I'm gonna figure it out.
All right. So I think there's 2 of these on the homework. All right. So we can work through on the homework, and we can always have more kind of practice on. That's no big deal. As I said, we've got COVID numbers. We've got those COVID tests we can change. There are actually several different COVID tests that are out there. Do what? Methamphetamine? Hold on. At home. Oh, hey, this is popping up. Meth test at home, sensitivity and specificity. So yeah, well, we have to. I'll find these out. I'll get these numbers, and I can post them so you can try them. Yeah. All right. So as I mentioned, the pregnancy tests are actually really good. So if you ever go to them, go grab them. They're going to be advertised as over 99% accurate. So the question is it worth it to do one of the $20 or $30 ones? I don't know, I guess they're 40 or 50 on some of them. Or can you get by with the dollar store pregnancy test? All right. So under ideal conditions, the tests have a specificity of approximately 100%. Has a sensitivity of approximately 100%. Pretty darn close to 100% on both. Under non-ideal conditions, which is
typically the at-home user, the specificity will range from about 77 to 94%, and the sensitivity at over 90%. The reason for the difference is user error. So we didn't even address user error in any of these tests. All right, these are just the tests we assume that there is no user error. All right, so if you follow directions and use it correctly, if that test comes back positive, you are like 99.9% pregnant. Not 100%. Can't prove, can't get perfect, but it is. If it comes back positive, it's pregnant, and that's across the board. So I knew that going in, and when we had, when my wife, was pregnant with our firstborn, she came in and surprised me or whatever, and asked, "How much did you pay for it?" So I did the $20. I didn't think it made sense to go cheap or to go like super expensive, so I went middle of the road. I said, "You spent that much on it? You should have did the dollars." I was more ticked about that than the fact that I was going to have 20-some years of payments coming out of my wallet. But no, the dollar store, if it comes back positive, it's positive. Most of the user errors on those are either not being able to read it correctly. So they're making them simple, but 1 line or 2 lines. I don't know how you can mess that up, but people do. All right. A negative or a plus sign. Again, I don't know how you can mess it up, but people do. Or it clearly says, I guess you put it in the urine because it's picking up the antibodies or the hormone, human gonadotropin. Put it in the urine and then you like let it dry. I would bet some people do that and then they rinse it off in water. They think that's gross. Again, that's the user error that happens. If you follow directions and do it correctly, that test is really, really good. All right. So we wish all tests were like that, but they're not. All right, so we talked about this Bayesian versus frequentist approach. This is the idea. This is why we work with it, and that's why more and more people are going for it. So if you collect your data and you're trying to make a conclusion, people want to say, not that, yeah, this is true or false, but I'm X confident that we're making the correct decision. So that's, kind of repeat this slide again, just to bring it back to, yeah, this is our frequentist approach, or this is the Bayesian approach. All right. So, and I give another example, and I think we went over these earlier on. Questions? I think we're going to stop here. We do have the homework, it's posted. You can work through it, practice it. I would probably wait till maybe tomorrow to try to do the Bayesian, these types of problems, those last 2 on that work. So I know if you do it now, it's real fresh, and you'll probably breeze through it. But if you give it a day and then come back and look at it, it might force you to get back into your notes and say, okay, let's double check I know how to do it, and that's kind of one more learning step to kind of drive it home. And then I'll have a couple more examples that I can post if you wanted to work on it. So I don't know if I'll post those on Blackboard. If I remember, I will, or if I'll just bring them to class and give them to your class. What we're going to introduce are probability distributions next, discrete distribution, binomial, and Poisson distributions. All right.